Audio Jungle. Audio Jungle.
So here now we'll talk about the degree of reaction. Like last class we had seen the specific work input to the compressor. We had seen the stage temperature rise. We had seen the stage pressure rise. Okay, or pressure ratio across the stage that we had seen P03 by P01. Now, very important parameter called degree of reaction. So basically the degree of reaction will be used for the turbo machines, not for only compression, for turbine also. This degree of reaction basically used, and this parameter will basically tell us like the workload sharing by the rotor and workload sharing by the stator individually. Okay, individually, like what percentage of the work is what shared by the rotor, what percentage of work is what shared by stator, and what percentage of work shared by the rotor. Why I am saying work, it can also be in terms of enthalpy, it can also be in terms of temperature. So if you say in terms of temperature or enthalpy, so what sharing of enthalpy shared by rotor, and what enthalpy rise percentage in stage shared by the stator. So rotor and stator both will rise the static enthalpy. Yes, we had seen in last lecture. So in that term, basically we'll talk about the enthalpy. So degree of reaction is the ratio of static enthalpy rise in the rotor to static enthalpy rise in whole stage. All right, and in one stage, rotor and stator is there. So based on this, we have to, because this is very important parameter. Okay, just like that percentage, that temperature rise, stage temperature rise, as in stage pressure rise. Similarly, we have a degree of reaction. So in axial flow stage, definitely that pressure rise will be in both rotor and stator. So here degree of reaction, it is denoted by capital R. Okay. So whatever the static enthalpy rise, static enthalpy rise, it is because of both stator and rotor. Okay, you had seen that table. You had seen that table, yes or no? In table you had seen, last lecture I had shown you that table, and in that table you had seen what static temperature rise or static enthalpy rise in both stator and rotor, right? So you can say the degree of reaction also provides a measure of extent to which the rotor contributes to the overall static pressure rise in stage. What percentage has been shared by the rotor in terms of that static pressure rise, because temperature rise you can say, or pressure rise, both will be the same thing, because if there is a rise of temperature, definitely there will be pressure rise. Okay, so both things you need to understand, and this whole it and comes to this stage, that so now in this case here if you define the degree of reaction, so whatever the degree of reaction, it will be in terms of both, in terms of static enthalpy rise in rotor to the static enthalpy rise in stage, or it is also in terms of uh, that enthalpy rise could be replaced by static pressure rise also. That will be the same thing. In few books you may get static pressure rise. Okay. Also like static pressure rise in rotor and static pressure rise in stage. So that meaning will be same. Okay. There should not be any kind of confusion. All right. So degree of reaction, it is ratio of static enthalpy rise, static enthalpy rise, or I can say pressure rise. Okay, pressure rise in the rotor to static enthalpy rise or pressure rise in whole stage. Done. So now this is the whole stage. This is what rotor and this is what stator. Okay. Now this is 1, 2, 3. So if I say what is this R, so you can say this R is nothing but what is the static enthalpy rise. If you remember that plot also I had given TS plot. So there you can write the static enthalpy rise delta H in rotor divided by delta H in stage. S for stage, R for rotor. Okay. This also you can write. This also you can write. What is the rotor? Rotor is 2 and 1. So definitely if you go this, so if you check, this is the point which is 1 and this is the point 3 and this is what 3 dash, this is P and S. Okay, so the whole stage is what between 3 to 1, but where is the rotor? Rotor is 2 to 1. So you can say this is H2 minus H1 rotor divided by stator, sorry, stage is nothing but between 3 to 1. So S3 minus H1 is nothing but stage, and H2 minus H1 is nothing but rotor, right? Now, so this also you can uh, divide this rise of the enthalpy in rotor and stator. You can write in this way. This is what enthalpy H and this is the entropy S, HS. Okay, I can say the pressure line what we have, this is 1, 2 and 3. These are the pressure line. Here we can say this is what P1 pressure line. This is P2 and P3. Where it is? This one is P1, P2 and P3. Alright. Now for this three pressure line, we have the division of rotor and stator. So one, this is called isentropic. So I can say this is 1, this is 2 and this is what? 3 dash, 2 dash. Okay. Where is the actual? This is the actual. This is the 2, this is the 3. Alright. Now if you check the division of it, so you can say this value, this is H2 minus H1. Okay. And this part H3 minus H2. Okay. And here this part is nothing but H3 minus H1. Hope this one is clear. Okay. So now this is the rotor, this is a stator and this is the stator. Okay, in short I have given, so this will help you to recall everything. Okay. Now so if I write the delta TA, which is the static temperature rise, in the rotor, and delta TB is the static temperature rise in the stator. Okay. So if I say stage temperature rise, so it will be delta TS and it is nothing but delta TA plus delta TB. Okay, always remember. Now this is the one thing in short, because the value will be asked to you, so everything you should clear, no? There should not be any confusion. So what is degree of reaction R, which is nothing but static enthalpy rise in rotor divided by static enthalpy rise in stage. What is the rotor? Rotor is nothing but H2 minus H1 divided by what is the stage? H3 minus H1. You can write in terms of temperature. So what is the H2? It is CPT2. So and CPT1 and similarly CPT3 and CPT1. So CP cancel out. So you can write T2 minus T1. it is T2 minus T1 divided by T3 minus T1. Alright, this you need to remember. Now, if you check what is the work, so the work if you write, then the work will be in terms of Cp at delta T, yes or no? So you can write work input, it is Cp delta Ts. Yes, we had seen in last class, and this is also by the formula it was UCA tan alpha 2 minus tan alpha 1 or UCA tan beta 1 minus tan beta 2, right? So now also you can say, because you are writing W input, so this Cp is nothing but delta Ts, and this delta Ts is nothing but whatever the temperature rise in rotor plus whatever the temperature rise in, here it is mentioned, rotor and stator, and then it combined, then it will be stage. Okay, this way. All right. But if you recall last class, I had explained whatever the work input to the stage, or you can say whatever the work input to the compressor, so it will transfer to the or it will be related to the rotor, because stator is stationary. So whatever the work you are taking, that compressor is taking for turbine, so that work is what basically required to rotate the rotatory blade, and that is nothing but rotor. So you can say whatever the work you have now, here you can write why this background is required, because in between if problem will be asked, then you need to answer in this way. Since all the work input to the stage is transferred to the air by means of the rotor. Okay, by means of the rotor. Hence, by SFEE. What is SFEE? A steady flow energy equation. If you use this for what? For the rotor, then what you will get? You will get W input is equal to that temperature rise in rotor. What is that? Delta T A. Delta T A in rotor. See here. So Cp delta T A and plus that change in kinetic energy in rotor, it is C2 square minus C1 square divided by 2. Alright. So this will be the steady flow energy equation. Alright. Now everything you have here. Okay. Now based on this we'll go and we'll derive the equation. So if you check here, degree of reaction, for degree of reaction you have here. So From here we can calculate that Cp delta T. What is the Cp delta TA? It is nothing but, check, work input formula you have. What is the work input formula? It is UCA tan alpha 2 minus tan alpha 1, or one more step I need to write. It is minus, what is the formula? Ct square minus C1 square by 2. Okay. Now check this. Cp delta TA, work input I have written here. This is nothing but anyone, in terms of anyone you can write. I am writing in terms of alpha 2. So it is UCA tan alpha 2 minus tan alpha 1 minus Ct square minus C1 square by 2. If you check the velocity triangle, we have this velocity triangle. In short, I am drawing this. This is C1, this is W1, CA, this is what, alpha 1, beta 1, this is what, exit triangle, and this is what, C2, alpha 2, W2, beta 2, this is what, CA. Rest you know, this is what, U, and this is also U. Velocity triangle, you are now aware with this. If you calculate C1, so what is the cos of alpha 1? It is cos of alpha 1 is nothing but Ca by C1. So what is the C1? C1 is nothing but Ca cos alpha reciprocal is sec alpha 1. Similarly, you can write C2. What is the C2? Ca sec alpha 2. You need to keep here. If you keep this, then Cp delta Ta you will get. It is UCA tan alpha 2 minus tan alpha 1. Okay, and it will be minus 1 by 2. Ca you can take common, it is square, so Ca is square, in bracket it is C2, so sec square alpha 2 minus sec square alpha 1. This is the value. So I am not going to open this and just write each and everything. Just two steps more I will write. Ultimately you will get Cp delta Ta. What is the Cp delta Ta? U Ca tan alpha 2 minus tan alpha 1 minus 1 by 2 Ca square. If you open this sec square alpha 2 and all, then in terms of tan it will be tan square alpha 2 minus tan square alpha. Check it. So ultimately we got, what is the Cp delta Ta? It is UCA tan alpha 2 minus tan alpha 1 is minus minus 1 by 2 A square tan square alpha 2 minus tan square alpha 1. Okay. Now what is the degree of reaction you have seen? The temperature rise in rotor Yes or no? The temperature rise in rotor, because whatever the formula you have here, the same formula you are going to use is, what is the R? R is nothing but this enthalpy rise in rotor divided by enthalpy rise in stage. Or you can also write enthalpy rise in rotor divided by enthalpy rise in rotor plus enthalpy rise in stator. Remember, this is stage, so in stage rotor and stator both we have. So you can say, what is the enthalpy rise in rotor? It is delta H. In terms of temperature, it is Cp delta T. In rotor, what is the temperature rise? Check. It is delta Ta. See here, it is delta Ta divided by, what is the enthalpy rise in rotor? It is Cp delta Ta plus, in stator it is Cp delta Tb. Okay, so your R is nothing but delta Ta divided by delta Ta plus delta Tb. Now this one is clear, okay? If they have given separate, they mention, okay, temperature rise in rotor is this and stator is this, then what is the degree of reaction? Then also you can use this formula and you can calculate. This is the one thing, but I will tell you what is this R. R is nothing but, if you check here, it is Cp delta Ta divided by this formula I'm seeing here. Cp take common, then what will be the value? Cp common delta Ta plus delta T. This is Cp delta Ta divided by Cp. This delta Ta plus delta Ts is nothing but this stage. Okay. Now you know R is nothing but Cp delta Ta. It's okay. But what is this Cp delta Ta? It is work input. This is also one formula. If they have given temperature rise in rotor only and they have given the work input to the compressor, I mean stage, then also you can use this formula. Okay, both formula are important. Now you understood, Cp delta Ts is work input. It is already mentioned somewhere. And here, see. So this is the another formula. Now if you write, this is the one thing. Second thing, if you write alpha 1 beta 1 alpha 2 beta 2, then how to write this? So you can write R. R is equal to Cp delta Ta. Just now Cp delta Ta you have calculated. See, this is the Cp delta Ta. So you will write, this value is nothing but UCA tan alpha 2 minus tan alpha 1 minus 1 by 2 Ca square tan square alpha 2 minus tan square alpha 1 divided by work input. What is the work input in terms of alpha 2 alpha 1? See, this is Cp here. See, this is the work. Any formula you can write. You can write in terms of alpha 2 or alpha 1 or beta 1 beta 2. Anything you can write. So I will write in terms of alpha. So this is nothing but UCA tan alpha 2 minus tan alpha. Alright, done. Now if you check, this is what it is. You can say R. This part is, if you check, one more step need to write, otherwise UCA tan alpha 2 minus tan alpha 1 minus 1 by 2. See, this is x square minus y square. So what you will get? Tan alpha 2 minus tan alpha 1 in bracket tan alpha 2 plus tan alpha 1. Take separate. Use CA denominator. Tan alpha 2 minus tan alpha 1, and this will be separate. Use CA tan alpha 2 minus tan. Ultimately you got R. It is 1 minus here we have CA square. I forget to write CA square. So it will be CA cancel out. So you will have CA by 2U in bracket alpha 2 minus alpha 1 will be cancel out. So you will have tan alpha 2 plus tan. This is very powerful formula. Very powerful formula. Okay. So they will give that value. We need to remember this formula. Okay. All right. Now this is the formula in terms of alpha 1 and alpha 2, and we also know the formula in terms of beta 1 and beta 2. Okay, so if you calculate in terms of beta 1 and beta 2, then this R value you can replace this uh, CA by 2U you have here. Okay, and alpha 2 plus alpha 1. So if you remember tan alpha 1 plus tan alpha 2, that relation I had given in first class. So based on that, we had, if you remember, it was U is equal to CA in bracket tan alpha 1 plus tan beta 1, and U is equal to also it was CA tan alpha plus tan beta 2. I had given this relation if you remember. So use this relation. What you will have? You will have 2U, directly I am writing 2U by CA, because U by CA is equal to tan alpha 1 plus tan beta 1, and similarly U by CA is equal to tan alpha 2 plus tan beta 2. If you add both, then what you will get? Tan alpha 1 plus tan alpha 2, here tan beta 1 plus tan beta 2. This you will get. Simple. So in this formula, what we have, R is equal to, here if you check, we can write at that result tan alpha 2 plus tan alpha 1. So what will be the value? R is equal to, see, R is equal to, it is 1 minus, it is 1 minus CA by 2U. Okay, CA by 2U, and it is tan alpha 2 plus tan alpha 1. What will be the tan alpha 2 plus tan alpha 1? It will be 2U by CA minus tan beta 1 plus tan beta 2. Check it. R 1 minus, take this multiplication inside, it will be minus 1, then minus minus plus CA by 2U tan beta 1 plus tan beta 2. This is also very powerful formula. This both will be cancelled out. This both. this value will be cancel out, 1 1 plus minus. So what you will have, this is very powerful formula, Ca by 2u in bracket tan beta 1 plus tan beta. So two formula you have, one is R is equal to 1 minus Ca by 2u tan alpha 1 plus tan alpha 2, and this is formula number 1, this is formula number 2. One is in terms of alpha 1 alpha 2, another is in terms of beta 1 and beta 2. All right, both are very very important formula because question they are asking based on both. Okay. Done. Now if you check this formula also in different way, R is equal to, they have you can write this Ca by u, it is tan beta 1 plus tan beta 2 by 2. Yes or no? So like it is tan beta 1 plus tan beta 2 by 2. So it is sometimes you also can write average, average of that two angles. So they may give this type value in way in this way also, Ca by u tan beta mean. Okay, this is also the formula. All right, one more formula I will give to you in the same way, just like you have alpha 1 alpha 2 beta 1 beta 2, you also you can derive by your own. Third formula if you derive here, then you will get R is equal to you derive it, you will get 1 by 2, this I am not deriving, Ca by 2u in bracket tan alpha 1 minus tan beta 2. So this is one more relation, and this relation is what? Very powerful. It is alpha 1 and beta relation. You just manipulate, you will get this. This is equation 1, I can say. Second, what we have, R is equal to Ca by 2u tan beta 1 plus tan beta 2. This is the second formula. And third, in the starting only you had derived, it is R is equal to 1 minus Ca by 2u tan alpha 1 plus tan alpha 2. All three formula are very special. Okay. So this was required to derive. Why? Because this result is what very important. Output is very important. It's okay, but in between also they can ask question like whatever each and every steps I had done here with respect to the temperature rise in rotor and stator. Separately, suppose they have given okay temperature rise in stator or rotor is this and work supplied to the stage is this, then what is the degree of the acceleration? So this formula will be used. If they have given temperature rise in rotor is this and temperature rise in stator is this, then rotor plus stator will be states, then this formula will be useful. Understood? So for that reason only, and if they have given in terms of velocity, so this is also the work input to the compressor, then velocity they have given and whatever the temperature rise in rotor is given, then this will be the formula. So each and every steps actually it is important, and this is also very important formula. If they have given degree of reaction, if they are asking degree of reaction and they have given the data, temperature T2, T1 and T3, T1 they have given anyhow. So this formula will be useful that time. That time, okay. If they have given temperature T1, T2 and T3, so that time degree of reaction formula will be this. All right, so now based on this degree of reaction, we have two types of the blading, okay. Okay, blading in space, and the two types are basically, one is called symmetrical blading, symmetrical blading, and second one is the unsymmetrical. Unsymmetrical blading, okay. Now, so if you talk about the symmetric blading, so what is the mean of it? Simple. See, if you talk about the symmetric blading here, so I will, and this blading in stage is what based on R, which is degree of reaction. So based on degree of reaction, if you go through it, so we have degree of reaction R. What is the formula we have? If you check one formula we had, which is nothing but R is equal to 1 by 2 Ca by 1 minus C, 1 by 2 minus Ca by 2U tan alpha 1 minus tan alpha 2, tan beta 2, right? So based on this, if we have R is equal to 1, if we are writing R is equal to 1, which means it is 50% degree of reaction. Just approximate number, means a random number I am taking 1 by 2. So and we'll check this 1 by 2 degree of reaction, what will be the relation, okay. So what is the mean of it? 50% degree of reaction, what is the mean of it? Because you know degree of reaction is nothing but this is what rotor and this is what is stator. So whatever the enthalpy rise or temperature rise in rotor divided by temperature rise in rotor plus temperature rise in stator, this is the mean. If I said degree of reaction is what 50%, so what is the mean of it? Its meaning is simple. Delta R is equal to, check, delta TR, temperature rise in rotor divided by temperature rise in rotor plus temperature rise in stage. If I said okay, if I said degree of reaction is what 1 by 2, then when you will get 1 by 2? Check. If this delta TR rotor, temperature rise in rotor is equal to temperature rise in stage, if it is same only, then it will be 1 by 2, right? What is the mean of it? temperature or pressure. And this is what is static. Remember it, static temperature or pressure rise in rotor and static temperature or pressure rise in stator. If these two value will be same, then only it will be 1 by 2. Yes or no? It's simple only. If both values are same, then delta TR is equal to delta TS. So you can write delta TR by delta TR plus delta TR. Delta TR common in numerator and denominator, cut 1 upon 1 plus 1, 1 by 2. So this is the only reason. Now you understood this whole concept, why we are keeping 50% degree of reaction for the most of machine. If we are not exactly keeping 50%, we are keeping degree of reaction nearby 50%. So both rotor and stator will be equally burdened. Equally burdened means both are doing the same work. Huh? Delta TR and delta TS means temperature rise in rotor and temperature rise in stator. If both are same, that means both are doing the same work. Both are equally burdened. Otherwise, if temperature rise in rotor will be very high and temperature rise in stator is very less, it means over the rotor blades, more work is what there, or it is more stressed because it is rising more pressure and more temperature. So for the healthy turbo machinery system, we always try to keep 50% degree of reaction so that our rotor blades and stator blades will be equally burdened. Is that clear? This point is very important actually. So sometimes it happens in interview also, directly they will throw this question, why 50% degree of reaction required for the turbo machine? So this is the only reason, because in this situation, if 50% degree of reaction we are having for any turbo machine system, then it means, if it is compressor, then it means temperature rise in rotor and temperature rise in stator, or you can say pressure, static pressure rise, or you can say enthalpy rise, but in rotor and stator's blade, it will be equally distributed. That's the mean of it. Hope this one is very clear to everybody. Okay. Now, so if we are keeping this 50% degree of reaction, then what should be the design angle? Okay, what should be the design angle for the rotor and stator, or what should be the blade angle and flow angle condition? So we have to keep this R is equal to 1 by 2 in one equation. We can keep here. We can keep here. Then what will get? Check. What is the formula we have? R is equal to, we have R is equal to, and R is equal to, that formula we have, R is equal to uh, R is equal to, it is 1 by 2 minus CA by 2U, okay, and this is what, tan alpha 1 minus tan beta 2. Alright, now if you are keeping this R is equal to 1 by 2, R is equal to 1 by 2 if you are keeping, then it is 1 by 2 minus CA by tan alpha and CA by CA by 2U tan alpha 1 minus tan beta 2. So what you will get? You will get this result. What is this result? If you check, because 1 by 2 will be cancelled out, and you will get tan alpha 1 minus tan beta 2 0. Tan alpha 1 is equal to beta 2, or we can say alpha 1 is equal to beta 2. When you will get this, when you have r is equal to 1 by 2. And what is the 1 by 2? 0.5. What is 0.5? R is equal to 50%. Means 50% degree of reaction if you have, then this relation you will get. They are asking in exam. Frequently direct question they are asking to you that relation. If alpha 1 is equal to beta 2, then what will be the relation? Alpha 1 is equal to beta 2. Okay. Now, if alpha 1 is equal to beta 2, then what is the next relation? The next relation will be same, beta 1 will be alpha 2. Yes or no? If alpha 1 is equal to beta 2, then beta 1 will be alpha 2. Simple only. Okay? Yes or no? If you check the relation, what is the relation we have? U by Ca is equal to tan alpha 1 plus tan beta 1, and U by Ca is equal to what we have? Tan alpha 2 plus tan beta 2. So what we have? Tan alpha 1 plus tan beta 1 is equal to tan alpha 2 plus tan beta 2. Yes or no? What will be tan alpha 1 minus tan beta 2? If you write tan alpha 1 minus tan beta 2 is equal to it is tan alpha 2 minus beta 1. Yes. And here you have this value, tan alpha 1 minus tan beta 2 is what? 0. So if you keep this value is equal to 0, so that means tan alpha 2 minus tan beta 1 will be also be 0. If it is 0, then what it indicates? The same thing, alpha 2 is equal to beta 1. Two results you got. For the 50% degree of reaction, for the 50% of the degree of reaction, you got alpha 1 is equal to beta 2 and alpha 1 is equal to beta 2 and alpha 2 is equal to beta 1. Now we'll draw the velocity triangle. In actual, what is the velocity triangle what we have here? This is the velocity triangle, right? If you check, this is what? C1, this is W1, this is CA, this is CT1, this is WT1, this is beta 1. Now exit triangle, if you check, this is alpha 2, this is beta 2, this is C2, this is W2, CT2, and this is W2. Now this is the general triangle. Okay. Now if we have R is equal to 1 by 2 or 50% of degree of reaction, then what result we got? We got alpha 1 is equal to beta 2 and beta 1 is equal to alpha 2. This result we got, right? Previous. Check, beta 1 is equal to alpha 2. Now based on this, if you draw the triangle, then what you will get? Anyway, you draw it straight. I'm not able to draw it straight, but it's okay. So this value, this is what? Alpha 1, and this is what? Beta. Listen carefully. So this alpha 1 will be equal to beta 2. So this angle and this angle must be same. This is beta 1 and this is what? Alpha 2. So this value will be T2, W2, WT2, CPT2. This is WT1, CT1, C1, W1, and don't forget this is what? CA. So CA is constant. Now if beta 1 is constant, so this WT1, can you say now this CT1 will be equal to alpha 1 is beta 2, so this CT1 will be, can we say now, this result also is useful. CT1 is equal to this value, because CA is constant, so this length must be equal to this length. Similarly, B1, beta 1, sorry, beta 1 is WT1, okay, because CA is constant, so this length WT1 and this CT2, because alpha 2 is beta 1 and alpha 2 is constant, so this, can you say this is what? WT1 is equal to CT2. Both result they had asked in your GATE exam, and very frequent question they are asking, like based on this, okay, this result. Okay, and this type of triangle called as blading of the stays called symmetric blading. This type of blading called as symmetric blading. This is the input and exit. Both are symmetric. All right. So that blading, in the sense of blading, okay, this is called symmetric blading, because U is constant, so whatever the value of CT1, it will be equal to WT2, and whatever the value of WT1, it will be CTT2. Okay, and this result you will get in general. This is in general. This result you will get when the degree of reaction is what? 50%. Okay. The same velocity triangle you can draw in this way also. So what is the common for this in this velocity triangle? If you check what is the common, so obviously base is common, that is true, but CA, that is the axial velocity, that is also common for both triangle, inlet and exit, both triangle. CA is the axial velocity which is common in terms of the vertical height, you can say, and the horizontal, what is the common? U is the blade speed or rotational speed. Okay, because u1 is equal to u2 and that is constant, so u1 is equal to u2 is equal to u, that already I had discussed in my previous lecture, so no need to go into that. I just want to draw this triangle in this way also, because they are in GATE question, if you check many question they had given in this way. This is what? Constant, and this is nothing but u. Okay, this is what u. Now we need to fix the base, because CA is the axial velocity which is also constant, so we can consider as that apex, common apex for both. So now can draw like this. Okay, and this height is constant, so I can draw okay, whatever this length will be this length. It is required to understand because they had given in your gate exam, they have given this type of triangle. Anyway, fine. And we'll have okay. Now check. We need to check this basic triangle, you need to check, and you can recognize which one is the inlet and which one is the exit. This is the inlet and this is the exit. So based on this, see, I can say this one is our inlet triangle, huh? This one is our inlet, so this angle will be what? Alpha 1. This will be what? Beta 1. And you just compare with this, so this will be beta 2 and this will be alpha 2. So this will be beta 2 and this will be sorry sorry, right? Rest everything is what known. If this is alpha 1, so obviously this value will be C1, this value will be W1, and this value will be W2, this value will be C2, and somewhere they will give to you this common value. They will give this velocity sometimes, and what is this velocity? CA. Check, CA is common for all both triangles. So this is also the velocity triangle. Okay, this is also velocity triangle, no? While you are solving suppose problem, then you do, because question they will give sometimes. Okay, so here it is symmetric. Okay, why? Because alpha 1 is equal to beta 2 and alpha 2 is equal to beta 1. For that reason, if it is symmetric, then if you want to show symmetric blading, then you can say this value, this one is equal to this one, okay, and this value is equal to this value. All right, anyway, just for your acknowledgement, what is the mean of unsymmetric bleeding? So unsymmetric bleeding, I will draw the diagram only, not more explanation required for this unsymmetric bleeding. Okay, now if you have suppose Okay. Obviously this will be U, no doubt. And this will be a common, okay, common, this height will be CA, okay, but this angle will not be same. Even you can see and in first look also you can say it is not same, but general diagram I am drawing so you can understand. Alpha 1, beta 1, beta 2, alpha 2. Similarly this is beta 2, this is alpha 2, alpha 1, beta. So here this you may say this is what R is greater than 50%, and obviously here you can show that beta 2 is greater than alpha 1, and here you can say this is R which is less than 50%. So definitely beta 2 will be less than alpha 1. Huh? By seeing this only. So this is not same, but if beta 2 is equal to alpha 1 and alpha 2 is equal to beta 1, then it will be symmetric. So this is the unsymmetric. In this symmetric blading, what we have alpha 1 is equal to beta 2 and alpha 2 is equal to beta 1. Okay. And this is what unsymmetric blading. All right. Anyway, so if suppose in terms this is beta 2 greater than alpha 1 when R is what greater than 50%, and in terms of if you want to write in terms of the velocity component, so definitely CT1 will be less than WT2 because beta 2 is greater than, hence WT2 will be greater than, and here beta 2 is less than alpha 1, so T2 it will be less than CT1. So that relation you should know, otherwise not required, but yes, this result is very powerful. Okay, this result is very powerful, this one. So make a important point here. Okay. Right. Now coming to the conclusion, because this part is almost done. Degree of reaction we have almost finished. The 2 points we need to discuss, that is nothing but R value. R we have, if suppose 1 by 2 which is 50%, this part is what done. That physical meaning also we understood. What is the physical meaning? That rotor and stator both are doing the same equal work. That's the mean of 50% degree of reaction. Second, this is the first one. Second, I just want to uh, go for this analysis that if R is what 0, and third, if R is what 1. First of all, if R is what 0, this type of machine called impulse machine. What it is called? Impulse machine. Okay, like Pelton wheel. Pelton wheel is, it is impulse machine. R is equal to 1. This is called reaction machine. Okay. All right. Now this is the different type of machine based on degree of reaction. We can say, okay, this is the R is 0, then it is impulse machine, and R is 1, then it is reaction machine. But what is the relation? What is the formulation? So formulation, if you check, R is equal to, we had seen that a temperature rise by the rotor divided by temperature rise by stage, and in stage we have rotor and stator. All right, just see here. And in terms of pressure also, pressure rise in rotor divided by pressure rise in rotor plus pressure rise in stator. That also you can say. Now, in terms of pressure also you can say, or if you say, I will write here delta P pressure rise in rotor divided by pressure rise, static pressure I am saying, static pressure rise in rotor plus static pressure rise in stator. Okay. Now, if I say R is equal to 1, okay, it's 0.2 I think, 0.2. If R is equal to 0, so see that formulation, pressure rise in rotor divided by pressure rise in rotor plus pressure rise in stator. So what is the mean of it? If R is 0, it means delta PA, pressure rise in rotor, delta PR, pressure rise in rotor will be 0. Obviously, temperature rise in rotor will be 0. Okay. If degree of reaction is what 0, then whatever the pressure rise or temperature rise, it will be 0. So whatever the pressure or temperature rise, it will be in stator only. It will be in stator only. Delta TA divided by delta TA plus delta TB. So it means delta PR, or previously I told you delta T temperature rise in rotor will be A. So this part will be 0. So it means only static pressure rise or temperature rise in only stator if R is 0. This is also for 1 marks. 1 marks theory question they can ask. Okay, for turbo machine they say directly, if degree of reaction is 0, then what is the mean of it? So you need to tell, you need to mark the answer. Check this option if it is given in terms of temperature, if they have given in terms of pressure, okay, or if it is like in terms of alpha beta also. Suppose the given, now if you find in terms of alpha beta, see what answer you will get. Check the formula. If R is 0, check the formula, any formula you can check. If R is 0, then what will be the relation? Okay, if R is 0, check, you can get here that tan beta 1 plus tan beta 2 is equal to 0, and that tan beta 1 is equal to minus tan beta 2. Huh? Yes or no? So magnitude wise beta 1 and beta 2 will be same, but angle wise it is just opposite, then only R will be 0. Okay, and it means it is working like one channel only, because stator will be working, rotor is not working. That's the mean of it, or it is not rising pressure. So you can say that magnitude wise beta 1 and beta 2 will be same, but angle wise beta 1 and beta 2 will be just opposite. Yes or no? That is the one thing. Now and that is the relation between angle. Okay, now here in terms of pressure and temperature, this is the relation. Now third point will go. What is the third point? If degree of reaction is what? 1. So here I had given the formulation, the same way you can analyze. Okay, now you are eligible to do this. So R is nothing but temperature rise in rotor divided by temperature rise in rotor plus temperature rise in stator, or you can say that pressure rise in rotor divided by pressure rise in rotor plus pressure rise in stator. If degree of reaction is 1, then what is the mean? When you will get this? Okay, so this value you will get 1 when the delta T will be 0. When the delta TB means 0 means pressure will also be 0, pressure rise. So what is the mean? What is the delta TB or delta PB? This is the pressure and temperature rise in stator. Means in stator there is no pressure rise or temperature rise. So it means only static pressure temperature rise in only rotor. Only rotor. Now if R is 1, if R is 1, then pressure and temperature rise in only rotor, hence it is called reaction machine. And this, hence it is called impulse machine. Okay. In terms of angle, check when R is equal to 1. Is there any relation, direct relation? So when R is equal to 1, check this third formula. When R is equal to 1, then 1 cancel out, so you will get tan alpha 1 is plus tan alpha 2 is equal to 0. So again the same thing, alpha 1 and alpha 2. That alpha 1 and alpha 2 is what? Flow angle. So magnitude wise, that flow angle will be same, but it is just opposite by nature. Maybe 30 degree minus 30 degree. Okay, maybe 45 degree minus 45 degree. Similarly, for the degree of reaction, if it is 0, then that time beta 1 and beta 2 magnitude wise it is same, but by nature it is opposite. Maybe minus 30, 30, 45, minus 45, 60, minus 60. I think this analysis is what sufficient for you. It is just like a thought opener what I am just explaining here, because you can do by your own. This is the simple 9th standard mathematics, na? It's not biggest thing, but it's just like a thought opening. So if I explain one time, so now you can think in that way, because if question will be asked to you, so you may able to answer that. That's all. Okay, so done.